Hello, today we're going to talk about building and executing GOMC simulations. And we're going to do this, we're going to create the simulations using the MoSDeF software. My name is Brad Crawford. I would like to thank Wayne State University and NSF for support for this research. NSF specifically for these grant numbers here, which includes grant for GOMC and for MoSDeF, and as well as the Wayne State College of Engineering. So first, we're going to go over some definitions. The simulation engines that we're going to talk about are GOMC and NAMD. GOMC, more specifically, we'll mention NAMD just briefly. GOMC is the GPU optimized Monte Carlo code, and it has a charm style formatting. And the NAMD is a molecular dynamics code, and it also has a charm style formatting. And what we mean by charm style formatting is just the way the files are formatted is similar to the charm program style of files. The simulation file builders, such as PackMol, which is a program that basically packs molecules into a box. So it takes a single replica of a molecule and just duplicates it and packs it into a box that is user specified dimensions and other parameters. VMD, or Visual Molecular Dynamics, is an analysis and visualization tool developed for many different engines, but specifically developed for NAMD. Other engines can use it just as well. It takes different file formats. It's a very versatile tool. MoSDeF, or the Molecular Simulation Design Framework, is basically a tool that enables generation of the initial files to run a simulation. There's four main types of files required for the GOMC and NAMD simulations. The first of which is the PDB file, which we're primarily interested in the coordinates from the PDB file, and that is the X, Y, and Z coordinates in any given simulation or simulation box. It also contains the atom name and number, and also the residue name and ID. There's some other parameters in there as well. The PSF file primarily contains the bond connections in the molecule, and these are the bond angle dihedral and improper connections, which are listed for every molecule in the system. It also has the atom name, type, and number. The atom types are used in conjunction with the parameter file to know which potential energy equation constants to use for that given atom or bead. It also contains the residue names and some other parameters, which we're not going to get into in this video. The control file basically tells the simulation engine what to do. So in this case, for example, it sets the temperature, the pressure, the type of the simulation, and the length of the simulation. In Monte Carlo simulations, you can also specify the ratios or percent of times to use each moves, and some other parameters and settings. Basically, anything you can tell the simulation to do, more than likely you're doing it through the control file. The parameter file contains a potential energy equation constants, which are also called force fields in this instance. So this basically just pairs an atom type with a parameter, and that is the bond angle and dihedral constants of the system. And with those, you can calculate the potential energy of the whole system. Why do we run Monte Carlo simulations, and what can they provide? So importantly, today, we can use the MoSDeF software to quickly, cheaply, and accurately generate a lot of simulation setups and configurations, and even with different MODIs attached and building on the molecules as we go. And what this allows is it allows for future large-scale screening of molecules, which means we'll be able to screen a vast array of different types of molecules and test them, get their physical properties or whatever other properties we wish to attain pretty quickly with minimal human interaction. And so why is this important? Because these simulations can predict the physical properties and phase behavior of pure components and mixtures. And right here, we look at some examples of what we can do. So in some of our past work, we showed that we can predict distillation curves of different fluids. And basically what this is it's just a loss of liquid volume. And the temperature here is basically the boiling point. So at this loss of volume, what is the boiling point of that fluid? And it's from 0 to 1, and 1 meaning there's no liquid left. And we can also get the liquid vapor equilibrium, which is the temperature versus density curve. So you got the vapor on this side and the liquid on this side, and then this point is just the average, with the critical point being here. And we can also get the pressure versus temperature, or pressure versus inverse temperature to be more specific. And we can also estimate the critical point. Now, it's important to note these critical points are estimated, and these open points, the non-critical points, are actually data points from the simulation. We use the open boxes to calculate the critical point. So it's also important to note that these are not the only properties you can get from Monte Carlo simulations. You can do a lot of other things like absorption and zeolites, for one example, and many other things, which we're not going to go to entirely in this video, but I just wanted to hit on some of the things you could do. The past GOMC workflow is quite cumbersome and has a lot of interconnection. And it's not typically easy for new learners to grasp because it's quite complicated. So we'll go through this here briefly. So basically, the first step would be to build your own molecule by hand. This is just one molecule of each type. If you have multiple different types of molecules, you'll need to build multiple ones so you have one unique of each. And you can do this by hand using VMD, or you might be able to find a downloaded version of the file you need. Either way, you got to use one method to create it. And then basically you use those unique molecules, you write a script that PackMol can read, and then you use PackMol to pack it in a simulation box. So you can see I had two different types of molecules here, you know, the blue one and the red one, and now they're packed into a box here of my specification of number of molecules. And then you take this, so you basically just have the coordinates or the PDB file here. And then you have to get or generate by hand a charm topology file, which this contains the bonding information, you know, the atom typing, the atom names, which are all important in the charm style topology. So you use this file, which it could be existing, you might be able to find a copy, or you have to edit it by hand. And then you combine these files using VMD, and then you come up with a simulation box that is now a PDB and a PSF, which means it has the coordinates from the PDB and the bonding information, all the bonding angles, dihedrals, and impropers from the PSF file. And then, and to get to here, you have to write another script or modify an existing script at least. And then once you have this information, you can create the GOMC control file, which this is typically in the past has been done by hand. And you have to enter some of the information like the file names in this file by hand. And basically the computer has to know where these files are located. So then once you set this up with all the temperature, pressure information, etc., how many steps to run, you also need the parameter file or the force field file. So you need to know what the potential energy equation constants are. So Many times you'll probably be able to find an existing file, but if you're doing something special or different, you might have to generate this by hand. So you have to add this, and this data has to be entered in the control file as to where it is located. And then finally, you can execute the GOMC simulation by executing run on this file, and then you can run the GOMC simulation. Now, this is not it probably as easy as I described it here. It takes quite a bit of understanding to actually realize how to do it, because you have to learn how to run VMD, PACMOL, and then edit all these files by hand, as well as know how to write all the scripts to do this. So for a new user, it can take a considerable amount of time. And if you want to learn more about how exactly to do this or better instructions, there's some information in the GOMC manual, but you can go straight to this website from GOMC and you can learn about how to do this process this way. However, the MoSDeF GOMC workflow is much simpler and it lowers the barrier of entry to new users significantly. And I will say that this same workflow can be used to run NAMD for non-protein simulations. So you have to, the residue name has to be the same as the whole molecule. So for example, a protein has multiple different residues per molecule, and right now how this program's set up, it will not work. But if you don't want to run a protein simulation, you basically can use this to run NAMD for anything you want, as long as you write your own NAMD control file now, because that is not currently available in MoSDeF. But aside from that, you can run NAMD the same way I'm describing how we can simulate GOMC and generate the boxes via MoSDeF. So basically, we use the MoSDeF package mbuild, and mbuild calls some other packages for MoSDeF like Foyer to help along with this. But from mbuild, we create a Python charm object, and then this charm object is able to write the PSF and PDB files, the parameter file, and the GOMC control file. So basically, once all this stuff is done, all you got to do is hit run on the GOMC simulation. However you do that on your desktop, on a supercomputing cluster or HPC center, that's up to the user. In the same way, in NAMD, we can generate the PSF and PDB files automatically and the charm style parameter files. And these are virtually the same for GOMC and NAMD, aside from the fact if you're using fixed bonds or angles in any molecule, GOMC is slightly different. We're going to go over an example of building the GOMC files that are required for a simulation using MoSDeF. Firstly, we'll import the packages we need from Python here. And then we will set the force field, get the molecule, and name the residue. So here, we're just going to get the force field that we want. In this case, we'll use the OPLS AA force field. And since we're using the OPLS AA force field, specifically an all atom force field, we can simply use a smile string to pull the molecule or create the molecule. In this case, pentane is represented by 5 C's here as a string. So we just enter this. We don't need to build the molecule in any other way. It just builds it from the smile string. And then we apply the force field to pentane and name the molecule residue, PEN, short for pentane. And now we have a pentane molecule to add to the simulation box. Now, in this case, we're going to run a Gibbs ensemble simulation or GEMC simulation. So we're setting up to do a liquid vapor equilibrium. In this case, we're going to build a liquid and vapor box initially with pentane. And to do that, we're going to select the compounds, a number of compounds. Now you can select the density as well for an all atom system and the box size in nanometers, which we're going to do 4.5 nanometers or 45 angstroms in each direction. And for the vapor box, we're going to do the same, a slightly less number of molecules, and then an 8 nanometer box and all the X, Y, and Z dimensions. And you can build the box with as many compounds or as many different compounds as you want. And you can select the ratio of compounds and the density, or actually select the number of compounds itself, depending on what you want to do. And then we need to build the charm object. So to build the charm object, we select the liquid box here, which is the box 0. And this is required for all simulations because you need at least one box to generate the charm force field. And for a second box, which is optional to use the charm object, is because for an NPT or NVT simulation, you only run a single box, but for Gibbs ensemble and grand canonical ensemble, you need 2. So this is optional. You can always put those as none if you're running an NVT or NPT simulation. So we'll always need the force field file name for a GOMC simulation. So this is user input, whatever you want to name the file. And then the force field selection, which we said before, we're using OPLSAA. And then the residues, all the residues in the compound in a list. In this case, we just do pentane.name since we named it PEN, and that's what it will give us. In the case of UA force fields, you want to rename some of the bead names to just C, so you can get a unique representation, because it'll number it C1, 2, 3, 4, 5 as it goes down through, and that gives you unique naming representation for the boxes. And for the GOMC simulations, you can also fix bonds or angles. If you wanted to in water, you just select the residue name in a list here and write them down, and it'll automatically fix it, which is fixed in the force field file or .imp file. But in NAMD, you would not want to do this because that is controlled in the control file. So from that, to write the force field file or .imp file, PSF and PDB file, we simply run these commands, and then that writes all the files directly from the charm object. And then lastly, we want to create the GOMC control file, which is done by selecting charm object, whatever we want to name it. And then the ensemble type, there's only certain ensemble types, which you can see, number of steps, and the temperature in Kelvin. And then the options that we want to use here, I want to use the switch potential, and then here's the variables that change in the switch potential. Now, all of these are typically set as standard default, except in the case, I believe, of the grand canonical ensemble, where you have to select a residue, a dictionary with a residue and a chemical potential or a fugacity, which just can't be set automatically because it's very specific. Lastly, for the OPLSAA force field, we use a geometric mixing rule or geometric sigma. So we want to set that to true. It's standardly set to false, which means you use just a normal average sigma, not a geometric sigma, or the LB mixing rules. Using the easy 2 pages of Python script that I just described, which is much simpler than doing it the old way. So we just open a terminal window and then go in and cd to the directory with the files we created. And then assuming you have the proper Python environment set up and active, or running in your base Python environment, whatever you have it set up to do, you just run the Python command with the Python file name that you want to run. And then after that's completed, you run or execute the GOMC command to run the GOMC simulation. You just select the full path with the binary file at the end. And that binary file is specific to CPU or GPU, whatever you want to run. On my desktop, I run GPU because I have a graphics processor unit that's compatible. Or on the HPC cluster, I would typically run GPU. if I'm doing charges in the system, i.e. if there's partial charges. If there's no charges, CPU is pretty efficient for GOMC. So this would just be changed depending on what you want to do and what's available. And then this option selects number of CPU cores you want to use. And then finally, the GOMC control file name that you'll be reading the input and or instructions on how to run the GOMC simulation. And then here we're just signifying that we want to output all the data to a log file name, to which can be named anything you really desire. And then we're going to go through an example running this in a terminal window. We'll show you simply how to do that. So here's the terminal window I have already opened. Here's the commands that I just went over. And then here's the file folder where we'll be accessing. So for the first command, the cd directory, if you don't know what the entire directory is, to get in this folder, I can simply type cd and then drag it into the terminal window and drop it there and hit enter, and that'll put me right in the directory that I want to go to. And then I'll just click in here. So here's the file name that we're going to run. So if I don't want to copy it directly, I just type Python, and then we'll copy the name, paste. And then when I hit enter, you can watch the files building in this area. It takes a little bit for the molecules to be packed into a box and parameterized. You can see it's working. It didn't find any impropers, which is okay because there's no impropers in this system of pentane. Once we get all the molecules boxes built, the force field files in the GOMC control file, we can finally execute the GOMC simulation. And as shown previously, we're only going to run 100 steps. Simulations typically runs for millions or hundreds of millions of steps, but for the sake of time for the video, we're only going to do 100 steps. And this script that is running is the exact same script that I'm showing here, just this 2 pages of Python script that we got running. It just executing in the background. It should be done any second now. As you go through, it lists some of the information. So I'm associating this residue or molecule with the OPLS-AA force field. Now you can select different force fields for different residues, i.e. molecules for GOMC or NAMD, but I stress that you know what you're doing, because mixing force fields can be dangerous if you are mixing different types of force fields that are not compatible with each other. So just user beware on that. So we can see all the examples or files are built here, the PDB for liquid and vapor box, PSFs for both, and the force field file, and the GOMC control file. And then to run the GOMC control file. Now, if you don't know where this is, you can find it in your folder and then drag it in to the terminal window to locate it if you want to do it that way. But in this case, I know where it is, so I copied it in and it's running. So we're running the GOMC simulation right now. And you'll see the output.date file. It's all log data. And then we're outputting these files for GOMC. One important file that most people use is the bulk data output file here. And I'll open it once the GOMC simulation is done. It shouldn't be too much longer. but the PDB files can be useful if you're doing analysis that is dependent on the actual atom positions. So we'll open the liquid file. The property is the steps, you know, heat of vaporization, volume, density, pressure. You get some of the averages there for the 100 steps that you ran. And that's pretty much it. We built and ran a GOMC simulation with 2 pages of Python script and executing it through a terminal window. All right, thank you for watching. Here are the references we used for the video.